We often take for granted, the incredible precision that underpins our modern world. Things like microscopic medical instruments or the structural integrity of skyscrapers.
Absolutely. Huge structures.
But how do engineers actually quantify the forces involved, to ensure safety, make sure things work, drive innovation?
Yeah, that's a great question. And it often comes down to these sort of unsung heroes.
Which is our topic today. Load cells.
Exactly.
So our mission in this deep dive is really to unpack what these crucial sensors are, how do they do their amazing work, and maybe importantly, why picking the right one is, well, sometimes it feels like an art as much as a science.
Precisely. And for you listening, whether you're, deep in technical specs already, or maybe just curious about the engineering marvels hidden around us, this should hopefully give you those aha moments.
Right. A shortcut to understanding without getting bogged down.
Yeah, we want to show you what load cells can really do, give you a solid understanding, but, skip the heavy jargon where we can.
Okay, so let's pull back the curtain then. At their heart, what are load cells, fundamentally?
Well, fundamentally, they're the core component for measuring force. Simple as that, almost.
Okay. These elegant little devices designed to do something pretty remarkable.
Yeah, the real brilliance is in that conversion process. It's what's called transduction.
Transduction, right.
It meticulously converts a physical force, could be tiny, could be huge, into an electrical signal. A very linear, measurable signal.
And that's what lets engineers quantify the unseen stuff, like tension or compression.
Exactly. Tension, compression, pressure.
Yeah.
It allows you to measure it with incredible accuracy because of that electrical signal.
Okay, and here's where it gets really interesting for me. The how. How does that conversion actually happen?
Right. So most high-precision load cells use something called strain gauges.
Strain gauges? Heard of those?
Yeah, they're tiny sensors, really microscopic, and they're bonded onto a specially designed metal part inside the load cell. We call that part the flexure.
The flexure, okay.
So when you apply force, push or pull, that metal flexure bends or deforms just a tiny, tiny bit. Sometimes only like a few thousandths of an inch.
Wow, that's small.
Oh yeah, imperceptible usually. But that minute deformation, that's exactly what the strain gauges detect. They sense it as a change in their electrical resistance.
Ah, okay. So the bend changes the resistance.
Precisely. A tiny proportional change in resistance. And that gets translated into usable, highly accurate data.
That's clever. It really highlights why the flexure itself must be so critical then, the metal bit.
Absolutely paramount. The design, the shape, the material used for that flexure, engineers optimize all of it.
Based on what? What factors?
Well, things like the load capacity needed, how much force will it see, the physical size, where does it need to fit, temperature changes, altitude even.
Altitude.
Really? Sure, air pressure can matter in some highly sensitive measurements. And critically, how sensitive it needs to be to forces coming from the side, what we call extraneous loads.
Right, because force isn't always applied perfectly straight on in the real world.
Exactly. It's a real balancing act between material science and mechanical design. It's quite intricate.
So when we talk about load cell designs, is there one that's sort of the classic? The go-to?
There definitely is. If you picture a load cell, you're probably picturing the low-profile design. It's pretty iconic.
Low profile. And Interface, the company, they actually invented the first one.
They did, way back in 1969. It was genuinely revolutionary at the time.
Wow, 69.
Yeah, and they trademarked it as the low profile. This innovation really did transform the industry and help cement Interface as a global leader in force measurement.
And that design is still popular.
Hugely. Their 1200 standard precision low profile is still their most popular product, even today.
So what makes that pancake design, as you called it, so special?
It's the internal structure. It's kind of like having two shear beam cells, another type we might touch on, but arranged end to end in a circle.
Okay.
And that circular arrangement provides exceptional stability. It resists forces from 8 different directions, right at the center point where the force is applied.
8 directions. That's impressive stability.
It really is. And that's what made it ideal for high-precision applications, like in calibration labs or aerospace testing, where you need ultimate accuracy and repeatability. It solved a big limitation of earlier sensors.
And I guess there are other benefits, too. You mentioned it's popular.
Yes. The design gives you a higher electrical output signal, which is cleaner and easier to read accurately.
Better signal-to-noise ratio, maybe?
Exactly. And it has a much better fatigue life. It can handle being loaded and unloaded countless times without its performance degrading.
That's crucial for long-term testing or industrial use.
Absolutely. Plus, as we touched on, its inherent resistance to side loads, those extraneous forces, is excellent.
Which is vital in the real world.
Definitely. And Interface actually takes it a step further.
Wow.
They individually adjust each low-profile cell during production, specifically to minimize sensitivity to those extraneous loads.
Wow, each one.
Each one. That dedication to precision is why it's so trusted in applications where even a tiny error could be, well, catastrophic.
Okay, so the low profile is a major player, a real icon. But you mentioned other types, like shear beams. The world must need more than just one design, right? For different jobs.
Oh, absolutely. It's a huge field. Beyond the low profile, there's a whole ecosystem of different load cell types, each designed for specific purposes.
Like what? Give us some examples.
Okay, well, say you have really tight space constraints, but you still need to measure both tension and compression.
Right. Push and pull in a small spot.
Then the S-type load cell is often the go-to choice. Its name comes from its shape, like the letter S.
Ah, okay. Makes sense.
And that shape makes it really compact, great for fitting into OEM machinery or small-scale test setups where space is at a premium.
Okay, S-types for tight spaces. What about more industrial settings?
Yeah, for industrial workhorses, you often see shear beams and bending beam load cells.
Beams and bending beams.
Right. You'll frequently find miniature versions of these inside industrial scales, like platform scales or tank weighing systems. They handle those kinds of loads really well, ensuring accurate weight measurement even in tough factory environments.
So they're rugged but still precise for weighing.
Exactly. Now, if you need to measure really huge forces,
like heavy-duty stuff?
yeah, truly heavy duty, that's where canister and column load cells come in. These are the powerhouses.
Canister and column, okay.
Think massive forces. They're built for rugged, high-capacity environments. You might find them in, say, structural testing for bridges or buildings, monitoring stress over long periods.
Wow. So embedded in infrastructure.
Sometimes, yes. Or used in massive industrial presses or material testing machines where you're applying immense force. They're designed to take a beating and keep measuring accurately. Critical safety stuff.
That's incredible. And are there even more specialized types beyond those?
Oh, definitely. Innovation keeps going. You have things like load button.
Load button.
Yeah, they're ultra compact, like little buttons.
Yeah.
Designed for getting force measurements in really tiny spots, maybe in medical devices or robotics.
Okay. And load pins.
Load pins are clever. They actually replace existing pins or axles in machinery, like in a crane hook or a clevis joint.
Do they become part of the machine's structure?
Exactly. It's a very neat way to integrate force sensing directly into the load path without adding extra components or taking up space.
Yeah.
Very space saving.
That is clever.
And then there's a whole other level. Multi-axis load cells.
Multi-axis, so not just measuring force in one direction.
Right. These can measure force and even torque simultaneously in multiple directions, often 3 directions of force and 3 directions of torque, so 6 axes in total.
6 axes. What needs that level of detail?
Think advanced robotics, where a robot arm needs to understand forces from all angles to interact with its environment precisely.
Ah, like for delicate assembly tasks.
Or automation, crash test dummies, even developing haptic feedback systems, where you need to measure complex, multi-directional interactions. It's a huge advantage for those really complex applications.
It really shows the diversity. So, okay, we've covered low profile, S-types, beams, canisters, buttons, pins, multi-axis. What's the big takeaway for someone needing to measure force?
The big takeaway, I think, is that choosing the right load cell is absolutely crucial. It's definitely not a one-size-fits-all situation.
Right. You need to match the tool to the job.
Exactly. You really have to understand the specific conditions and the demands of your application.
So what questions should you be asking yourself?
Well, first, what's the capacity? How much force, max and min, do you need to measure accurately?
Okay, capacity. Makes sense.
Then space constraints. How much room do you physically have to install the load cell? Is it a tiny spot or is there plenty of room?
Physical fit. Got it.
Environmental conditions are huge. Will it be extremely hot, cold, wet, exposed to corrosive chemicals, dust?
All that can affect performance or lifespan, I guess.
Oh, absolutely. And finally, how long does it need to last? Is it for a short-term test, or does it need to operate reliably for years, potentially getting millions of load cycles?
Right, the duration and fatigue life.
Thinking through those factors, capacity, space, environment, lifespan, helps you narrow down the options and select the load cell that's going to give you the best performance and, frankly, the best value for your specific need.
It really drives home how application-specific this all is.
It really is.
So we've taken quite a journey today, haven't we, into this incredible world of load cells.
We certainly have. from understanding they're the heart of force measurement.
Yeah, that transducer concept.
Right, converting force to an electrical signal using those amazing little strain gauges bonded to a flexure.
And realizing how critical that flexure design is.
And then exploring the shear variety, the iconic low profile, the compact S-types, the industrial beams, the powerhouse canisters, and all those specialty types like pins and multi-axis sensors.
It shows how these devices, which can look quite simple from the outside, are really the silent backbone of precision measurement.
Absolutely, and innovation across so many fields relies on them.
Understanding them definitely unlocks a new perspective on how so much technology actually works, doesn't it? Those unseen foundations.
It really does.
Okay, so for your final thought, something to ponder. Consider this. How many everyday objects or really complex systems that you rely on are silently, fundamentally shaped by these unseen force measurements?
Yeah, think about it.
From, like you said, the tiny forces guiding a surgeon's robot, maybe the weight sensors in your car seat, all the way up to the colossal pressures being monitored in a skyscraper's foundation or a bridge. Load cells are these quiet guardians, making our world function safely, efficiently, and with just incredible precision, often completely without us ever realizing they're even there.
A silent fundamental role. It's quite something when you stop to think about it.